Okay, I start recording it, and yes, this is what we will study today. Oh, before I forget, we have a quiz that is due next week, by the beginning of the class. Okay, of course, if you are done, let's say you finish the quiz tomorrow, then you can just turn it in. Of course, please write it neatly and nicely, though. Okay, and the material will include uh, the topics that we discussed today. So don't try to do the quiz right now because it still includes what I have to cover today. Okay. Today we'll cover, continue from what we did last week on population variance. We will do some examples on how to compute it. And then we will go on to sample variance formulas and apply that to computation. Now let's do what we left over last week first. Suppose, for example, we have population data. Help me picking like maybe 8 numbers. Eight, 7, 5. Doesn't have to be different. You can pick the same number again. 8 again. Okay. 9, 3, 4, 5. 17. Or maybe I use 1 and 7. Okay. So this is population. The n is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, nice number. Good. Okay, and then the sum of x will be, we add all of them. That's 20 plus another 20 plus 17 plus 57. And the sum of x squared equals to 8 squared plus 7 squared plus 5 squared plus 8 squared plus 9 squared plus 3 squared plus 4 squared plus 5 squared plus 1 squared plus 7 squared. Please confirm what I have here. It's 383. That's what I get. So you square one by one in case you wonder what I did here. In case you wonder what I did here. This is 8 squared plus 7 squared all the way to square. This one here, it's basically just add those numbers. Okay, now once we are done with that, then what is population mean? Population mean is the sum of all the data divided by the population size, that's 5.7. Okay, and then the population variance will be the first number. I usually call that the yellow one. This is the blue one. This is the green one. Then I try to benefit from the coloring I can use here. You know, this is one of the advantage of doing it on Note instead of using whiteboard. You know. Okay, I try to kind of like think of something positive of doing distance learning. Okay, so this will be 10 times 383 minus 57 squared over 10 squared. That's 3830 minus 57 squared divided by 100. I get sigma squared equals to 5.81. A little note. Once we got that, standard deviation, population standard deviation, population standard deviation denoted by sigma without square is the square root of sigma squared. Okay, so if I continue asking what is the standard deviation, I basically take the square root of that number, which will be 2.4103. Okay. Now, in remembrance of what happened 19 years ago in the attack of United States, I would like us to take 5 minutes quiet time in remembrance of those who, how that attack actually changed America forever. Okay, let's take a 5 minutes quiet time, not a break. And if you don't mind, let me ask you to spend some time to read again what happened on that day. I will post some excerpt from Wikipedia. Please spend some time to remember what happened at the time. There's a big chance that some of you actually are not born yet or still very, very young at that time. And I would like you to know that it impacts so many people, including me. Okay, you can continue reading it on your own. And of course, it doesn't have to be Wikipedia one. You can see the recording, some recordings, a lot of recordings are on YouTube. How then this becomes the one of the main reason we have Department of Homeland Security. Okay, let's go back to our class. We have example one, when we have population raw data and we needed to compute the mean, variance, and population standard deviation. Now let's go on with what happened if the data, the population is given to us in form of a frequency distribution. Let's say I make a frequency distribution. Let's say this is the number of passengers, not including the driver, the number of passengers going to a parking lot. Let's say 35 driving alone, and then 27 cars driving with a driver with one passenger. And then this is 11, 3 passengers, let's say is 4. And then we want to find the population mean and population standard deviation. So what we will do first, we will find the population size first, of course, right? That will be 70. And then I extend the table it's for the first extension fx, and then for the second extension we have second extension is x squared and fx squared. So fx, the data times the frequency, this will be 0 here, this is 20, that's 22, that's 12, the sum is 54. Okay, so the mean is 54 over 70. 54 divided by 70 is 0.77143. Okay, so this is the number of the average number of passengers beside the driver of a car going into a parking lot. I just make up stories, okay? But this can be anything. Okay, this can be anything. This can be the number of children of a couple married in the last 5 years. You know, okay. Let me go on with the second extension. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, and then multiply by the frequency. Okay, I get these numbers from here. Let's say, for example, this 20 coming from 20 times 1. That gives me the 20. Okay, 11, the frequency times x squared give me that 44. Okay, so on and so forth. So then the population variance will be, I need to add this first. Oh, exactly 100. Right? Then that will be 70, the population size, times 100 minus 54 squared over 70 squared. Population variance is 7,000 minus 54 squared divided by 70 squared. And it's 0.83347. I hope you follow me with calculator though. Okay, and tell me if I'm running a bit too fast. Okay, then the population standard deviation will be the square root of that number. It's 0.912945. That's the example on how to compute population mean and population standard deviation from group data single point. Now, let's move on further. How about applying this into finding the estimated mean and standard deviation of group data interval. I need to make up some stories again here.
Master, I have a question.
Uh-huh.
Can you go back up a little?
Yeah, okay.
So thank you. Where it says f of x, is that f times x or f to the exponent x? That's f times x, right?
That's f times x, yeah.
Okay.
That's f times x.
It kind of looks like f to the exponent. Okay, thank you.
Yeah. I have a cursive handwriting, so my f is like this, in which my line here, right? So it seems like it is to the power of x, but it's actually not. It's actually not. My f to the x will look like this. My f to the x looks like that.
Okay.
That's the exponent. Okay, but no, not
that's
that
what we
one.
got the last line, right? We times f and then x to the second power.
Yeah,
so
fx squared means f times the square of x. So
yeah.
Remember that this is not the same to fx being squared. No, it's not.
No, yeah, of course.
Okay.
Thank you.
Sure. Oh, by the way, do you guys know that I actually saved these notes and I put it on the discussion? Do you know that?
Yeah, I seen it.
Yeah. Let me show again. Is it this one? This is what we have earlier. This is not what I want to show. This is the one I want to show. So what happened is like the week we have last week, right? So after the class, I save it into PDF, so you can find the notes here. You can find the notes here. And I see that a lot of you already here, but do you realize that you need to sign in your attendance? Okay, so go to the discussion. Oh, hold on, my bad. I have not started mine though. No. This is not the one. I didn't do this one. I wonder if I can change the title. Let me just. Can I just change? Yeah, I will change the title. I will just change the title. So this is for discussion on. Oh, hold on. This is for last week, though. This is for last week. I forgot to do the one today then. Oh, my bad. Good thing I saw it. Okay, discussion. Quiz. By 8. So you can start working on the attendance. Okay, just do it now. Just do it now. Before you forget. While I will start working on writing some problems here. Okay, let's say the data be, what is good? From 3 to 5, 6 to 8, 9 to 11, and then 12 to 14. And the frequency be, let's say 7 here, 12 here, 14 here, and then 9 here. Let's say that's the population frequency distribution, and we want to find the population mean and population standard deviation. A little note before we really start. Our textbook, just like a lot of other textbook, recent textbook, our textbook gives the formula, computation formula for standard deviation first. Without going through the formula for variance. So they will write the formula for standard deviation, population standard deviation as square root of something quite nasty. And even that, they only give the formula for raw data. Standard population standard deviation for raw data. This is how they give it. Okay, but I need you to aware that there's actually no inconsistency between my formula and the textbook formula, because my formula approached that from variance first. Okay, this is the variance. So I teach from variance and then do the square root. Okay, and our textbook actually do population standard deviation right away without mentioning variance until much later. Okay, now I don't know about this edition though, but as I remember from the previous edition, that's what they did. Okay, so Thomas, can I just use that formula from textbook? You can, but why? Why? You want to carry that square root all the way? You know, why don't you just do the variance first and then apply the square root at the end, right? That would be easier. That would be easier. So we can focus on what happened in the radicand inside the square root and deal with the square root later. Okay? Then let's see. So how do we extend this? Let's add them up first. So 7, 9, 13 plus 9, 22. So that's 42. Now I would like you to do this. And the formula for population variance is population size, that's the 42, times the sum of fx squared, fxi squared, minus the sum of fxi being squared over n squared. That's the formula. So I already get the yellow part. Okay. I need the blue part here, which is the sum of fxi. That's the blue part. That's the yellow part. Okay. And this is the green part here. Okay, that's a fxi squared. So before I do the first extension, I need to find the midpoint first for each category, for each class. And then I multiply the frequency with that midpoint. Now after that, I do the second extension. I find the square of the midpoint before I go on multiplying by the frequency. Now let me give you 2 minutes. I know in 2 minutes you are not done with this table yet, but try to do your best. In 2 minutes, we come back. Okay, I will start. And you can just continue and then compare with what I have here. And let me know if I myself make mistake. This is 4, this is 7, this is 10, this is 16. Multiplied by the frequency 21, 84, 140.
For 7 times 4, or f times xi.
Oh, that's 28, huh?
Yeah.
Thank you. I need my calculator. I wish I can just use Excel, huh? During the test, if you want to use Excel to compute this, go ahead. Okay, and if you know how to use your calculator to compute all these numbers also, go ahead. You know, but in my opinion, if you can use your calculator and you can use Excel, your computer, just go with your computer faster. A lot faster. Seven times 16 is 100. 12 times 49. 1400. 9 times 169. 1500 plus 588 plus 12. That's 3,621. Am I okay, by the way? Anybody can confirm or tell me anything wrong with my computation here? Thank you for that 28 though.
I got the same answers as you so far.
Okay, good. And then, because if I make any mistake, then whatever I do from now will be wrong. Okay, then the mu will be 369 over 42. So you see your test one will be the first page or second page of your test one will be this kind of number crunching. That's 8.78571. And then as for the variance, let me do it below. Variance will be 42 times 3621 by 369 squared over 40 squared. 42 times 3621 minus 369 squared. Don't forget that the numerator has to be a positive number, or the minimum for the numerator is 0. Okay? And therefore, when you divide by the denominator, then the variance will always be positive, hardly 0, but never be negative. So once you see your variance is negative, something must be wrong in your computation. Okay? Something must be wrong with your computation if the variance is negative. Now, because the variance is positive, therefore, the standard deviation will still be positive, because the standard deviation is the square root of a positive number, or 0, of course. That's fine. Okay, in case you need to copy that down, go ahead. Now, how about sample variance? Sample variance. Now, for sample variance, just like population variance, we have definition formula and computation formula. Now, the formula for sample variance is very similar to population variance, but there's some change compared to what we have in the mean. When we have raw data, then sample variance notation is S squared. If you put notation here, S squared is equal to the mean of squared errors. Originally, it's supposed to look like this. Is it right? Originally, this the population version of variance in the definition formula. However, because of some technical reason, then we find out that this to be -1 here will be more accurate. Okay, they call it has something to do with degree of freedom, but forget about that for now. Okay, just remember the formula that instead of dividing by n, we divide by n-1. Then what happened with the computation formula? If you remember the formula from population variance, it looks like this. Supposed to be n squared. Well, originally for population variance, it looks like this. Originally, it's capital N here and capital N here, right? Okay, take a look if you happen to take the notes. Now, when it comes to sample, then I change that capital N becomes lowercase n, supposed to be n squared here, but one of the factor n on the denominator, I changed it to be n-1. Okay. Now, one of the big issue you will have later on when you take the test or quiz is, Thomas, how do I know it's population or sample? Well, read the question. Okay. Usually, I tell you in advance if it is the data I give you is sample or population. Now, in case it's not clear implicitly or explicitly that the data is sample or population, then use sample. No. If there is no, no clue on sample or population, there are times the wording tells us implicitly, not explicitly, if it is population or sample. But in case we don't know at all, then treat the data as sample. Okay, let's continue. How about if we have group data single point? Then the definition formula with which we hardly use will be, remember the trick last time? After the sigma notation, after the summation notation, we insert the F. You remember that? Okay, after the sigma notation, after the summation notation, we insert the F. Now, at this point, I hope you realize that you may have the formula, but still don't know what to do. Okay, you need to know how to read a formula and what it implies, not only what numbers or what the formula means, but also develop a procedure to come up with those numbers in the formula. We had before we insert this, and then now we insert this. We insert this when it comes to group data single point. And then when we get group data interval, we insert subscript 5. Okay, now if you want, you can copy these formulas down first. Now, I also hope then you understand why our textbook don't give all these 6 formulas. Our textbook just gives you the raw data formula. Okay, because what happened with the group data single point, group data interval, is basically such variation from there. Even though I still hope our textbook can emphasize how the variation being done. Okay. Our textbook didn't really do it clearly though. But you will see then the further you go into stats later on, when you need to do computations, they give you the formula for raw data, and then you develop yourself what happens if you have group data or group data interval. Okay. Let me quote one example we have earlier. Go with example 1. Call this example 1. B. And instead of population, I call that sample. This is a raw data case, right? Okay. Then what is the sample size? As I remember, that was 10. The sum of x was, what's that again? Sheet 57, 383. The sum of x is 57. The sum of x squared is 383. So what is the sample mean? Sample mean, exactly the same way to compute population mean. Of course, different notation, we get 5.7. Then how about sample variance? Sample variance will be, the numerator will have exactly the same numbers, 10 times 383 minus 57 squared. Let's compare, I will move this green here. You see what happened on the numerator? It's exactly the same. Okay, the change is on the denominator. The change is on the denominator. Instead of dividing by 10 squared, we divide by 10 times 1 less than that. Then when I use my calculator, I have sample variance to be 6.45556. Okay, so the procedure is very similar. The only modification happens on the denominator here. Instead of n squared, we have n times n minus 1. Okay, with that said, then we can see some very important observation that sample for the same data, then the sample variance, if you treat that as a sample, then the sample variance will be greater equals to the population variance. Actually, they're only equal if they are both equal to 0. Okay, if the variance is 0, then both sample and population will be 0. And the variance is 0 if all the data are exactly the same. Okay, yeah. So most of the time, if any data is not the same to the other data, then what you get is the sample variance is strictly greater than population variance. Okay, but for sake of conservative and to be safe, then I use equal sign there. Now, of course, then consequently, the sample standard deviation will be greater or equal to the the population standard deviation. Okay. So if I want to go on from here, what is the sample standard deviation? You do the square root of that number. I get 2.54078. Okay. If I go back to the notes I have above, oh here, population standard deviation. Okay, and for sample standard deviation, it is also the square root of the sample variance. Basically, standard deviation is the square root of the variance, regardless in which case. In case of population, in case of sample, the standard deviation is square root of variance. Now let's see example 2. I will call that example 2b. I will change this becomes a sample. Therefore, the notation for the means will be x bar, and the standard deviation becomes s. Then what happened with x bar? The way we occupy the table to the extension for the frequency distribution is exactly the same in both cases, sample and population. Then when it comes to the formula, that's when the notation will get different and the computation will get different also. 54 over 70, the sample mean and population mean supposed to be the same. That would be 0.77143. Let me make sure I get that number. Sorry, 77143. It's the sample variance will have slightly different. That will be 70 times 100 minus 54 squared over 70 times 1 less than that. Okay, so 7,000 minus 54 squared divided by the product of 70 times 69. Okay, 0.8455. Now, assuming you already have TI-84, let me show you how you're supposed to punch it in on your calculator. Yeah, on your calculator, this is how you will punch it in. Notice that this is basically the numerator is in a grouping symbol and the denominator also in a grouping symbol. So if you want to compute all of them all at once in your calculator, start with parentheses. This is the group for the numerator, 70 times 100 minus 54 squared, close parentheses. This is the group for the numerator. And then divide it by, don't forget, you need to group the denominator. It's 70 times 69. Okay. Now, what happens if you forget to use parentheses on the denominator? Let's see, what happens if you forget to use parentheses on your denominator? So let's say this is what you get. This is what you type. Then your calculator will divide the numerator by 70, and then whatever the quotient multiplied by 69. You see? Okay, because your computer doesn't know what you want to compute and just based on what you type in, right? Okay, see, when I press enter, the number is very, very different. Okay, and that's because you forget to use parentheses on the denominator. Okay, now I go over this because what I don't want to happen is like you don't even practice at home and you don't really see the difference when you use your calculator. Okay, be aware with this, you need to have that parenthesis. Okay. Now then, the square root of this will give us the sample standard deviation. That will be 0.91954. I believe last week I already mentioned, when it comes to decimal, give me at least 5 decimal places. If you need to round to 5 decimal places. Second, if there's no integer to the left of your decimal point, you need to write that leading 0. Okay? If there's no number to the left of your decimal point, you need to write that leading 0. So I will not accept, in fact, I will penalize half point if you write it this way. Without that leading 0, okay, I will penalize half point. You see what I mean? But Thomas, other teacher, okay if I don't write that leading 0. Well, then tell that other teacher he's supposed to listen to me. Or she has to listen to me. Why I'm the one have to listen to her or to him, huh? No. Well, each teacher has their own style, right? Okay, each teacher have their own style. The thing is like, why I have to listen to other teacher? Why don't you let other teacher listen to me instead? Especially if you are repeating this class, right? Especially if you're repeating this class, tell that teacher, maybe because of this, you are repeating this class. No, I don't think so. My point is this, You took another teacher, you don't make it, right? But you still want me to listen to the teacher that you are failing from. Oh, that's not nice, right? Okay. Each teacher, we have to respect the independence of each teacher. Okay, we call that academic freedom. Okay, so I can do what I want my student to do in this class, okay, and they can do what they want to do in their class, okay. But once you start telling me how I'm supposed to teach because other teachers do it that way, then I will tell that other teacher why that teacher didn't do it the way I do it, okay. So it's basically coming back to this, who should listen to who, right? Okay, keep it simple. The student should listen to the instructor, just like that. Keep it simple, okay? And it is that simple though. Okay, in the name of academic freedom, like I have control over my students, and no teacher have control over me in this class. Of course, I still need to follow the standard requirement for teaching, right? Okay, but this is about the technicality. Okay, other teacher can let you go without that 0. In my class, I penalize you if you miss that 0. But I have my purpose. It's not because I just do it because I want to be arrogant in this class. Here's the thing. In many cases, I have seen people, they write the decimal point so small, okay, and then let's say 0.0, and in the later step, that person actually coded as a 7 instead of 0.7. The decimal point is so small such that you don't copy that later, and then eventually from 0.7 becomes 7. You see, I don't believe in evolution until I see this. Okay, so if people ask me, Thomas, why you believe in evolution? Do I really look at the data from those bones? No, I just look at my students' handwriting. Okay, if so much can change in one page, why nothing can change in 100,000 years? Huh? It's by the way, that's not the argument. That's not the argument. If you remember a long time ago when you study algebra, let me give you the example that I see the most. It has nothing to do with decimal point. It actually has something to do with quadratic formula. The quadratic formula is supposed to look like this. Anybody remember this formula? Okay, if you don't worry. Okay, I just show you, but you have seen this before, right? For sure, for sure that for you to get to this class, you must have taken algebra 2 sometime in your past. Okay, And regardless you pass it or not, you must have seen this formula. Now the thing is, a lot of instructors and therefore a lot of students didn't realize that this line here covers the whole numerator. Okay, now because the teacher didn't emphasize that, or maybe the teacher emphasized but the student was not listening, then as the time goes on, people copy this formula, the line gets shorter. The line gets shorter. And eventually, the over 2a only covers the square root. You see, again, even people who don't believe in evolution turns to believe in evolution simply because the students work. If so much can change in one page, why not in 100,000 years? Right? Okay. But anyway, I'm not teaching you about evolution here though. And it doesn't imply I believe in evolution, okay? I'm just joking around that. If your handwriting can change so much in one page, then what makes you think that nothing can happen with your DNA in 100,000 years or even million years, right? Now, that 0 at the front, try to make sure that you actually see the small decimal point. Okay, that's my purpose. Okay, that's my purpose. And if you go to Kaiser Permanente, and actually if you are in nursing major, they actually emphasize the need of using this leading 0. Okay, the need of this using this leading 0. Imagine if you need to inject, you are told, okay, put this person to sleep and inject, let's say 0.15 milligrams of something to put you to sleep. Okay, and then because of your doctor's laziness, he wrote 0.15. And then when you inject that patient, instead of injecting 0.15 milligrams, you forget the 0, you inject 15 milligrams. How many times more potent is this? 0.15 and 15. 15 is how many times 0.15? So 15 divided by 0.15, that's what you do on your calculator. 100 times, okay? No wonder you originally want to put that patient to sleep for 2 hours, you end up making that patient sleep for ever, maybe. Okay, why? Your decimal point. And later on, do you blame the doctor? Well, the doctor wrote that decimal point there. Okay, are you willing to blame yourself? Right? Well, I didn't see that decimal point, then it's your fault, right? Okay. Now the thing is, if once somebody died, then you can punish whoever at fault, but it will not make that person raise again, right? No. So to prevent that from happening, then they try to build some self-correcting method, some self-correcting procedure. Okay, so 0.15, just to make sure you see that decimal point. So in future, if you see 0.15 as a nurse, when you see 0.15, what you will do? You will call the doctor, confirm, is it 0.15 or 15? Is that decimal point here? It's just simply a dirt. Okay? So you will ask the doctor to clarify. That's the reason I want you to use that leading 0. Okay. In fact, from nursing major, from nursing field, there have been some people die in the past. I think there were 7 people die in the past because of this kind of mistake. We definitely do not want that to happen to us or to our family member, right? Okay. But if you still think that writing this leading 0 to be something not worth that's penalizing half points, then you are actually waiting for a big disaster happening, and who knows, it happens because of your writing, right? No, I'm not saying that I wish that happened. No, I wish it won't happen, but it would be better if we have a built-in procedure to prevent that from happening. Okay. Let's go on with example 3. Let me call that example 2b here, and I will quote example 3, something that we have done earlier, right? So we don't need to redo the computation anymore. And at the same time, you can contrast how we create population variance and population and sample variance. Okay, suppose I change this now to be sample. So I want you to find the sample mean and sample standard deviation. Let me give you 3 minutes to do this. Oh, hold on. Something not really right there. It's kind of like change. I need to do that. But anyway, we get the numbers already. Okay, let me give you 3 minutes to compute what is the sample mean and sample variance, and then sample standard deviation. Okay, the sample the sample mean will be 369 over 42. This should be the same mean we have in the population case. It's 8.78571. And then sample variance will be 42 times 3,621 minus 369 squared over 42 times 41. I get 9.24564, whose square root is 3.04067. Okay, can anybody confirm my computation?
Also got the same.
Okay, good, thank you. So we have done the sample variance. Of course, you still need to have hands-on experience though. Okay, you still need to have hands-on experience. I recommend you to take a look in my quiz later on, the quiz that you need to turn in. Okay, and before you work on that, you may want to check this note first. Okay, check this note first and try to work out some problems from my old quizzes, right? Let's say. Or some solutions I have in the past. You may be able to see this also in our textbook, but our textbook way of showing it, they emphasize on the formula instead of the procedure. You know, the way I see the formula reflects the procedure. So don't just attack the formula right away. Okay, if you look at the formula, you may get confused though. Okay, focus on the procedure. From that formula, it reflects the procedure. So work on the procedure first, which is this thing here. Okay, then use those numbers from the procedures. from the extensions of the frequency distribution, then apply into the formula. Now, let me go on. Some early uses of mean and standard deviation. Now, if the data is numerical, and it's not too much skewed, then we use the mean to represent the center of mass. Let me show you first. Okay. Let's say the data is spread on this booklet here. Okay. Now, then the center of mass is basically one point of that data that you can use to represent the whole data set. Okay, so if I need to pick one point on this booklet to support the whole booklet without tumbling, what point will that be? Okay, what point will that be that I can pick and support that one single point such that the whole data, the whole structure actually can be supported without tumbling. Okay, that's what mean is. That's what mean is. In physics, we call that center of gravity or center of mass. Now, but more importantly is then beside picking one number to represent the whole data, the data set, how the data actually spread. Okay, it is being represented by the standard deviation. Now, there are two early uses of this mean and standard deviation. The first one, let me call that part A, Chebyshev Theorem. Chebyshev says the following: the portion of the data more than K standard deviation away from the mean. Away from the mean for K greater than 1. Is less than 1 over K squared. Now, let's try to picture what this theorem actually says. Let's try to picture what this theorem actually says. Suppose, for example, let's see what we have earlier. Let me use these numbers here. Okay, 8.8 and 3.0. Okay, so let, for example, the sample mean to be 8.8. Okay, and then the sample standard deviation is 3.0. Okay, now imagine a number line. Imagine a number line where you have 8.8 in the middle. This is the sample mean, right? Okay, and then let's say we go 2 standard deviation away from the mean. Of course, then we go to the left and we go to the right. Okay, so you plus standard deviation plus another standard deviation, that's plus 6, right? That's plus 6. So that would be 14.8 here, minus standard deviation, minus standard deviation, this is 2.8 here. Okay. What we meant by more than 2 standard deviation away from the mean is the number of data, the portion of the data that is greater than 14.8 and less than 2.8. Now, according to Chebyshev Theorem, less than 1/2 squared of the data set is in this region. Okay, less than 1/4 of the data set is less than 2.8 or more than 14.8. Okay, less than 1/4. So less than 25% of the data is less than 2.8 or more than 14.8. Okay, now another example. IQ score is known to have the mean of 100 and standard deviation 15. So the question, for example, what percent of the population, of the adult population, has IQ score within 70 to 130. Now, if you look at the number line, 100 is here. Okay. If you move twice standard deviation to the right, you get 130. This is the mean plus twice standard deviation. This is the mean minus twice standard deviation, that's 70. Okay. The one in question is what percent lies in this interval. That's the one in question. Okay, but we can use Chebyshev to compute what percent in this interval. Okay, by Chebyshev, less than 1/2 squared, which is 1/4, which is 25% of the population has IQ score not within 70 to 130. Now, I don't say it's 25%. No, I'm not saying it's 25%. I'm saying less than 25% is not within 70 to 130. Now, consequently, therefore, more than 75% of the population has IQ score within 70 to 130. Okay, so you can imagine when we say less than 25, let's suppose, just make up numbers, suppose a total of 20% here, which is less than 25%, right? Okay, then there must be 80% in between. Does it make sense? Okay. When outside of that interval is less than 25%, then inside of that interval must be more than 75%. Okay? So suppose for example, I changed the story a little bit, but I use the same number. Let's say Thomas average, class average is 100. Okay, Thomas class average is 100 with standard deviation 15. Okay, it means more than 75% of Thomas class actually score between 70 to 130. Thomas give a lot of extra credit, so much extra credit such that the average turned out to be 100 and standard deviation 15. Okay, so more than 75% of the, from this computation, we see that Chebyshev theorem says that more than 75% of Thomas students actually score within 70 to 130, which also means more than 75% score 70 or above, right? Can I say so? Now imagine if somebody then file a complaint against Thomas saying that most of Thomas students actually failed the class. Then I can just use the Chebyshev theorem. That's not right, you know. Even Chebyshev theorem, I don't need to see further. Just tell you that the mean is 100, standard deviation 15. Is enough to refute your statement that majority of students is failing Thomas class. Okay, just by Chebyshev theorem, I don't need to look into the detail of the data. Okay. Now, by the way, the reality is most students in statistics not doing well in my class. Okay, so I'm not a teacher. I'm sorry, I'm not a teacher who can give you an easy time to pass statistics. No. No, I'm not saying that I make it hard. No, I try to make it as easy as possible also. But at the same time, I want to make sure that when you pass this class, you can actually apply statistics into whatever you learn. Okay, like whatever your field. Statistics is being used a lot in psychology. Okay, in social justice, with the situation we have around us in the last 4 months or even 6 months. If you want to talk about COVID, then it will be 9 months already. A lot of statistics that we see, right? Okay, but when people give you statistics, first, do you know what it means? Second, can you tell if somebody's lying? Because people do lie using statistics. And somehow we have a mindset that if somebody can come up with a statistic, then that person must be being honest. No, people do still lie using statistics. Okay, they quote one number and not the other number. They quote one number and not the other number. You know, so once somebody, if you are well trained in statistics and you get this result here, okay, and you get this result, then whoever say that the majority of the population actually have IQ score less than 70 is something you can refute right away. We can refute that right away. Okay. No, it's not true. It won't happen under any situation. It won't happen. Okay. Now that's first Chebyshev theorem, and it doesn't have to be twice standard deviation though. You can make it 3 standard deviation. You can make it 1.5 standard deviation. That still work. Okay. That the portion of the data more than k standard deviation away from the mean is always less than 1/k squared for whatever k you have there. Okay, so the k can be 1.5. The k can be 1.2, as long as the k greater than 1. Okay. Now, part B, the second use of mean and standard deviation is called empirical rule. If Chebyshev theorem applies in any situation, that's why we say Chebyshev theorem is conservative. Whatever the data, once you tell me the mean and standard deviation, then I can apply this Chebyshev theorem. Now, when it comes to empirical rule, there's a requirement for the data to have before we apply this rule. The rule is if the data set is approximately symmetric and bell-shaped, then the following rule applies. Okay. The first one, let me tell you first what this rule says. First one, approximately, so you see, if this is approximately symmetric and approximately bell-shaped, such that it is also approximately, the result of approximation. Approximately 68% of the data is within one standard deviation away from the mean. Second, approximately 95% of the data is within two standard deviation away from the mean. And the third one, approximately 99.7% of the data is within 3 standard deviation away from the mean. Let me first explain what this hypothesis mean, what we mean by symmetric and bell shape. Now, we are talking about a data that is bell shape. Bell shape looks like this. That's bell shape. Okay, basically the mean happens at the peak, right? Okay, symmetric. So imagine if you fold the data along this line here, the left-hand side and the right-hand side match. Okay, if you fold it along that line. So when we say symmetric, that's what it means. It has an axis of symmetry. Okay, no, it doesn't have to be. It doesn't have to match precisely, though. We just approximately. Okay, just approximately. Okay, and when we say bell shape, it means the following. This is the mean, either x bar of mu, right? And the further you are away from the mean, the less likely for that to happen. Okay, the further you are away from the mean, the less likely it is to happen. And not only it is less likely to happen, it's less likely even more. Okay, so for example, the IQ score mean is 100. Okay, then it is more rare somebody to have IQ score 140 compared to IQ score 120. Okay, it's more rare somebody have IQ score 120 compared to IQ score 140. I'm sorry, 140 is more rare than 120. The closer you are to the mean, the more likely it is to happen. The more likely, the probability is higher. Okay, the further you are away from the mean, then the less likely it is to happen. And not only less likely, you see, like the probability for 120 compared to 110 is a lot more compared to 140 to 120. Now, what I want to emphasize is the following. Oops. You see, from 100 to 120 is 20 units. From 100 to 110 is 10 units. So this 120 is twice further from the mean compared to 110, right? Okay. Now, if the probability is decreasing, let's say by X%, then the probability for 140, which is twice more than 140, whose distance from the mean is twice more than the distance from the mean to 120, the probability here is even much less. Okay, let's say from here, I just make up numbers. Let's say the distance here is 0.4, it decreased by 0.4. Then the one here, not decreased by 0.4, multiplied by 0.4. Then the one here, you may multiply it by 0.3. In other words, the probability decrease even faster the further you are away from the mean. Okay, basically imagine bell shape. Okay, basically imagine bell shape. The further you are away from the mean, the less likely for that to happen. In fact, if you multiply the distance by 2, so 10 multiplied by 2 becomes 120. If you multiply by 2 from that 120 to 140, right? Okay, then it gets even less. Okay, it decreases a lot more compared to the one you had before. Okay, now that's what the nature of bell-shaped distribution. Now, like what I said earlier, this is approximately, right? That's approximately. So, that rule, empirical rule, actually says the following. Suppose I have a bell-shaped distribution. So hard to make it really symmetric. I try to make it symmetric. Okay, and this is the mean here. Okay, now if we go one standard deviation away from the mean, let's say this is the mean, and you add one standard deviation to the right and one standard deviation to the left. And suppose it is bell-shaped, then approximately 68% of the data is actually in this interval. Approximately. So using the numbers we have here, using IQ score number, oops, what did I do? Using IQ score number, and we know IQ score is bell-shaped. Right. So for example, IQ score is known to be bell-shaped. If you took this class before, then we learn the word normally distributed. One of the main characteristic of normal distribution is it is bell-shaped, such that now once we know the mean is 100 and standard deviation to be 15, then by empirical rule, approximately 68% of the population has IQ score between 85 and 115. Approximately 95% of the population has IQ score between 70, that's 100 minus twice the standard deviation, and 130, which is the mean plus twice standard deviation. Okay. So pictorially, if this is the IQ score and this is the distribution, this is the mean 100. If you go twice standard deviation to the right and twice standard deviation to the left, then approximately 95% of our population is in this interval. Okay. Now, I'm about to give you a break, but I want you to think about the following. Some mind exercise. Do you think approximately 95% of ELAC students has IQ score between 70 and 130? The answer is no. The answer is no. But I think the follow-up question is, is it more or less? More or less than 95%? Is it more or is it less? Okay, now I'm giving you a break. We come back at 10:15. And while you take your break, you go smoke, you go. Before I answer, is it more or less? Let's think about those people whose IQ score is less than 70 or less than or more than 130. So those whose IQ score more than 130, very likely they don't come to ELAC, they go to university right away. Okay, now I'm not saying that all of them will be like that. No. If their IQ score is higher, a lot higher than average, then there's a chance some teachers already identify them and they get the offer of going to university right away, very likely with some kind of with significant scholarship. On the other hand, if my IQ score is less than 70, there is a chance that I don't do well in high school, and such that I decide that going to school is not my best interest. Okay, that's therefore then East LA college students will be will consist of even more people with IQ score 70 to 130. Okay. Now, when I say somebody's may just go to with IQ score high may go to university right away, I'm not saying that those students, there's no such students at East LA College. No, that's not what I'm saying. Okay. In fact, I want to say that I have seen students whose, in my opinion, their IQ score is more than 130, and I found them at East LA College. Okay. And I found them at SMC. I found some at West LA College also. Okay, it's just like it's less. You don't really see students with IQ score more than 130 in college. Okay, those students, they tend to be identified a lot earlier and get a good scholarship package to university. Okay. But I also see students from other country, they are very, very smart, but they say, you know what, going to college is cheaper for me. And that's actually a smart thing, okay? And so instead of going to university right away, they say, you know what, you can hold that scholarship for me, you know, but I will go back there within 1 or 2 years. Once I'm done with my GE, the basic stuff, then I go to that good school for the higher level course, okay? Now, how about students who have IQ score less than 70? Now, IQ score is just intelligence score, okay? But simply means that it simply implies, not always anyway, implies this person will not do well academically, but it doesn't mean this person cannot do well in other field, okay? No. This person may have a hard time to study from academic setting, okay? But these people may still do well with other walk of life, okay? Now, of course, there are people who actually intellectually challenged, and that's why we are here for, okay? I'm not saying that they are less than us. They're still human. We still want to appreciate them as the same with us, right? But knowing that they are intellectually challenged, then we want to study more such that one day we can help people like them. Okay? Well, anyway, that's a little use of variance and standard deviation and mean, how we can approximate. How we can approximate the portion of our population, the portion of the data, maybe sample, and try to inference from there, get a summary from there, and what we can do for our population. So you will see that what we learn in statistics here is actually very, very useful in understanding first what kind of population we are dealing with. And from there, we can decide what is the best intervention to help people at the left-hand side of that curve. Okay, and I hope one day, if you don't become a business person who are rich, if you become a business person and rich, please remember we have people, we have part of our population, part of our society need some help. And I want you to be rich if possible, so that you can help. Okay. Now, don't worry. I'm not against rich people. I want you to be rich. If you can be really rich, don't forget me. Okay. Yeah. If you want to share your wealth with me, that would be great. But I'd rather you share your wealth with your the population around you. Okay. And I believe if one day you can be rich, you won't be like there must be people around you who, and of course your neighbors, also helping you to be in that position, in that situation, right? Okay, and another reason I want you to learn statistics, not only just to pass this class and transfer, but especially one day, if you become politician, for example, okay, you can think from this point of view also. The reason you are elected to be a senator or congressperson or the mayor or whatever it is, okay, is so that you become a public servant and help the society, okay? And how we use the resource around us to help people in need, especially, okay? Now that's for the early use, and we will see more use of that much later, especially in chapter 7 and chapter 7, 8, and 9. Now the next topic that we will go over is quartile system. Quartile system. Quartile system is partitioning or dividing the data set into 4 equal parts. Let's say we put the data in order, sorted data. Now, if you remember, once we put them in order, last week we learned about median. Now, median actually separate or partition the data into 2 equal parts. Some textbook use median, the notation for median capital M, but actually the correct notation for median is X tilde. Not X bar, it's X tilde. However, this notation is rarely used, mainly because when we handwrite this tilde and it's too small, we may misseen that as X bar. That's why we don't really use this notation, and the median will be just written as median instead of using any notation. Now, the median partition the sorted data into 2 halves. We call this lower half, and this is the upper half. Okay, so for example, when the government tell us that the median income of after the census, like we have census this year, right? And then they tell us that the median income is $67,000 annually. It means 50% of our population make less than or equal to $67,000 annually, and 50% make more or equal to 67,000. Okay, that's the interpretation of the median. Of course, when it comes to census, we deal with very, very big data, okay? And I use approximately 50%, okay? But that's very, very close to 50% though. In that case will be 49.9 at least. Now, quartile system, on the other hand, actually partition the sorted data further into 4 equal parts. Instead of only 2 halves, into 4 quarters. Okay, now what it does is actually get the median of the lower half, and they call that the first quartile, Q subscript 1, and the median of the upper half. That's the third quartile. Okay. Implicitly, the median is also called the second quartile, even though we don't really use that terminology. Okay, so to define it more formally, Q1, the first quartile, is the median of lower half. And that lower half not including the median. Now, Q3, the third quartile, is the median of the upper half. Not including the median. The median of the whole data. Okay, let's do some example. The simple one first. Suppose we have this data. I put it in order already, right away, sorted data. So if the data is not sorted, you need to sort it first. Okay, put it in order first. Let's say I have 14, 14, 15, 17, 17, 20, 21. We have 7 data here. We have 7 data here. Then the median is, we need to find the median first. We need to find the median first. To get the first and third quartile, you need to find the median first. Now the median is this guy, right? This 17 here, that's the median. Are you with me? There are 7 data plus 1 divided by 2, that's data number 4.
Yes.
Okay, now once you get the median, okay, then we can find the lower half and the upper half. This is the lower half and upper half. Now, when we do the lower half and upper half, we don't include the median, okay? We don't include the median. The median 17 here, we don't include that in lower half or upper half. Now, then we go on further. So what happened to the first quartile? Now, what is the median of lower half? What is the median of the lower half? How many data in lower half? 3 data plus 1 divided by 2, the second data. So the second data in the lower half will be the first quartile. Okay, and then in the third quartile, the second from the top, basically the second data of the upper half will be the third quartile. Okay, now then what happened if in this case, because we have an odd number of data, then the median is one of the data, right? Because we have odd number of data, then the median is this 17, exactly one of the data, and we exclude that from lower half and from the upper half. Now, what happens if we have even number of data? Let's say the sorted data is that 14, 14, 15, 17, 17, oops, 17, 17, 20. There are only 6 data. Then the median will be between two numbers, right? The median will be data number 3.5, right? So the median will be the midpoint or the average of the middle two numbers. So the median is 16. Right? The median is 16. Now that 16 is here. It's not one of the data. That 16 is here. It's not one of the data. So the lower half will be this guy is here. This is the lower half. And this will be the upper half. Okay, now then, what is the first quartile? Then look at the lower half, what's the median? That's right, that's 14. And how about the upper half, what's the median? That's 17. Okay, so to think about it, it's basically the following. You need to find the median of the whole data set first. Okay, you need to find the median of the whole data set first, and then from there, you get the lower half and upper half. Now, once you get the lower half, then you apply the median idea for that lower half again. And the third quartile, that's the median of the upper half. Okay, now the issue usually is, do we include, Thomas, do we include the original median? And the answer is no. We don't include the median of the original data. The original group, the original data set, okay? We do not include the median. Now, however, I need you to be aware that different softwares have different algorithm or different procedure. To find Q1 and Q3. Now, all these softwares will give you the same median, but some softwares give you different first quartile and the third quartile. Let me see if I can find it in our textbook. Let me see from our textbook. That should be there. And I hope I can just quote it for you. Give me a second. This is the, let me cut it off, screenshot that. Okay, so this is the excerpt from our textbook. There is no universal agreement on how to find percentiles and there is no universal agreement on a single procedure for calculating quartiles. Okay, if you use a calculator or softwares, then you may get result different from others. Okay, to be more precise, there is actually an agreement. Okay, there's actually an agreement. The agreement is the one I show you here. We don't include the median. Now, the thing is, some softwares is being used for a big purpose, and some other softwares being used for a smaller situation. Let me see if our textbook, or our textbook doesn't have that. I really want to look for an example. No. And I need to find it from other textbook. I'm looking at our textbook and I don't find what I want. So let me see from other textbook. Give me a second. Okay, I get this from the same author, but this is the 10th edition. Here's what it says, that different software. Suppose the data, this is, for example, suppose the data is, I sort it right away, is 1, 3, 6, 10, 15, 21, 28, 36. There are 8 data here, right? So the median is 12.5. Okay, now every softwares agree with that. Now, according to our procedure, which is the correct procedure, then the first quartile will be the median of this lower half, right? Which is 4.5. And the third quartile will be the median of the upper half, which is 21 plus 28 over 2, which is 24.5. Okay, now here's the thing. There are some statistical softwares. First one's called StatDisk. Now it will give you the same result. For Q1, Q3, if you use StatDisk, you get 4.5 and 24.5 for the first and third quartile respectively. If you use your calculator TI-84 or TI-83, you will get the same result. Now the thing is, if you use Minitab, or SPSS, these two are softwares that is especially designed for statistics. You will get 3.75 and 26.25 instead. Okay. The thing is, especially SPSS. SPSS is the, as far as I know, is the most powerful statistical software, statistics software available, and it deals with a very, very, very large number of data. Okay. Now, Minitab pretty much can do a big size data, like we call it big data. Okay. And therefore, because it deals with big data, the procedure they use to find the first and the third quartile is being modified to deal with large data, okay? To deal with a big number of data. Oh, by the way, SAS, another statistic software, also give us the correct one. If you use Excel, now I think it refers to old Excel, it gives us this number 5.25 and 22.75. I quote this from Triola. So Mr. Triola is actually doing this little research on different softwares, elementary statistics. The 10th edition, not 13th. In the 13th edition, I don't find it. It is on page 112. So give credit to him. Okay. Now here's the thing, though. Here's the thing. Why I mentioned this? Because I have found in the past, somebody tried to do my test and plug in all the numbers in Excel and find the first and third quartile. And that person complained to me when I marked that person wrong. Now, the thing is, Excel used different procedure, okay? Excel modified the procedures of what it's supposed to be to slightly different procedure, such that when you deal with only 8 data, it will give you wrong answer, okay? Okay, but Thomas, how about Minitab and SPSS? This is you say that this is a very, very powerful statistic softwares, but then why they give us wrong answers? Well, because this softwares here is designed to deal with a very, very large number of data. Okay, it's like you don't use a bazooka. You don't use a bazooka to kill an ant. You don't use a bazooka to kill a cockroach. Okay, now I don't advocate for killing animal. No, that's not what I'm doing. But even if you want to do so, you don't use a bazooka for those. Okay, that's a waste of bullet. That's a waste of effort. Okay, no, you don't. You just don't do it. Okay, so in other words, there's nothing wrong with the softwares. Okay, it's something wrong with how you apply the softwares with the type of data you have. If you have 8 data, okay, why don't you just do it by hand? Okay, if you have 40 data, okay, then put them in order and do it by hand. You don't need softwares for that. Okay, okay, you can use TI-84, right, if you want, the one I told you to use. If you have only 8 data, or if you have 40 data, if you have 60 data. But what happens if you have 4 million data? Will you use TI-84? No, you don't use TI-84 if you have 4 million data. Why? Because your calculator does not have enough memory to handle 4 million data. Okay, not to say to compute using those data, no. It doesn't even have enough memory to deal with them. Okay, so the reason one of the big reasons why I tell you this is because I want you to be aware that in my class, you need to use this procedure because this is the correct procedure. Okay. However, you may get different result if you use other softwares. Okay, because different softwares is being designed to deal with different size of data. Okay, Minitab SPSS deals with very, very big one. There's a new software called R. A new software called R. I think it's not really new, but it's actually more recent compared to the one we have here. Okay, and that will give us a correct result even if the sample size is very small or very big. Okay, that's something good about this software are the way they actually this software actually use the computation power of the memory. Okay, I mean, it actually used memory, bigger size of memory to help. So it can handle large data and still apply the procedure. Apply the procedure with V1. Okay, now with this said, let's apply this procedure to one of the problems I had in the past. Let's see. Give me a second. Let me look for my old tests. I've been teaching stats for too much, so I will be able to find data from my old tests. Okay, let me ask you to think about this. And what I want you to do is find the median. Find the median. And then from there, you find the third quartile, the first quartile, and the third quartile. Now, I already sort this data in the following order. I sort it this way. You see what I mean? Okay, and I think each column consists of 10 data. So here we have a total of 53 data. Consider this as a sample. So n equals to 53. Now, how do we find the median? And we use that formula, 53 plus 1 over 2. That's the 27th data. That will be your median. Data number 27. So 10, 10, 20, 1, 2, 3, 4, 5, 6, 7. Okay, so this number is our median. Then if data number 27 is our median, then how many data to the left of that data number 27? How many data here? How many data here? The lower half has n equals to, if this green one here is data number 27, then the number of data less than that will be, there are 26, right? Now then, the first quartile will be computed, will have this for position, 26 plus 1 divided by 2. That's 13.5. Then you look for data number 13 and data number 14. Data number 13 is this. Data number 14 is this. Okay, so before you compute the first quartile, you need to first know how many data is in the lower half. Okay, there are 26 data, then you use that formula 26 plus 1 divided by 2, give you data 13.5, means the quartile, the first quartile here is in between two numbers, and therefore you need to write it this way. That's 38.5. You need to write it this way and that. Okay. Now, likewise, the third quartile is data number 13 from above and data number 14 from above. Data number 13 from above, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so the third quartile will be the middle, the average between 79 and 79, which also be 79. Now, you know the average of two 79s is still 79, but I still need to write it that way. Okay. By the way, this question here, the one I quote for you here, comes from my fall 2016 test 1. My fall 2016 test 1. Okay, in case you want to copy that down. So you see in my examples above here, example 1 and example 2, we have raw data, right? In my side example here to show you what the first and third quartile are supposed to be and the different result you get if you use different softwares. And example 3 here is when you have larger sample size, but still raw data. Now, then what happens if we have group data? Group data single point. Suppose I make up numbers. Let's say this is X, this is F, 17 to 18, 7, 19, 12, and then 20, 11, 21, 10. So first, find the median. Now we did it last week. We do it again, and you will do it again in the quiz that you need to turn in next week. The number of data here is 42, right? Number of data here is 42. So to find the median, I need to look for the position first. 42 plus 1 divided by 2. That's 21.5 data. Now then I need to look for data number 21 and data number 22nd. 21st and 22nd. What is data number 21st? Look at the cumulative. Total of 2 here, total of 9 here, total of 21 here. So data number 21st is, the 21st data is 19, right? And 22nd data will be 20. Now, if you don't believe me, you can put them in order. 17, 17, 18, 18, 18, 7 times, right? And then 19, 19, 19, 12 times. And you will find, up to here we have 2 data, up to here we have 9, up to here we have 21st. Okay, then the 20-second data, the 20-second data will be the 20-second. The 20-second data is 20. So the first, the median will be, the median will be the middle between 19 and 20. Now, because the median is the 21.5 data, therefore, there are 21 data in the lower half and upper half. Now then, how about the median of the lower half? Then Q1, then Q1 must be 21 plus 1 over 2. That's the 11th data. Now, what is data number 11? Data number 11 is 19. Now, what is data number 11 from the top? Data number 11 from the top. The top 10 data is 21. The top 10 data is 21. Then the 11th data will be 20. The 11th data from the top is 20. Now, let me ask you to do this problem using this example here, in case that you want to, oops, in case you want to copy that, go ahead. But some thinking required here though, okay? Some thinking is required there. So let me grab the problem from the test. Let me ask you to try this one. So for example, I think this is example 4. Oh no, example 5. Example 5. Find the median. We did this before for the median. But more importantly now, what's the first quartile and the third quartile? Okay, let me give you 3 minutes from now. The total here is 40, is it right? Yeah, it's 40. So the position of the median is 40 plus 1 over 2. That's 20.5 data. So I need to look for data number 20th and the 21st data. Now data number 20th is 7. And then data number 21 is 8. So the median is 7 plus 8 over 2, right? That's 7.5. Now, because the median is data number 20.5, then there are 20 data in the lower half and upper half. Now then the position will be 20 plus 1 divided by 2. That's 10.5 data. So I need to look for data number 10th and data number 11th from the bottom. Data number 10 is 7. Right? Data number 11 is also 7. So the first quartile will be 7 plus 7 over 2, which is 7. Now data number 10th and 11th from the top. Data number 10th is 9. Number 11th is 8. Right? Okay. So if you list that from above, right? The top 4 is 10. The next 6 is 9. So that's 10 data right now. Okay. So data number 10 is 9. Data number 11 is 8. Okay, now that's how we get the median, which you're supposed to know already by this time, and the first and the third quartile. Notes? We don't find in this class first quartile and the third quartile for group data interval. Not in this course, not in this course. We can estimate it. If you go further into statistics, you can estimate it, okay? You can estimate it, but in fact, the way it is, the way other softwares doing it, right? Remember the third quartile for other softwares, okay? They actually do it as the modified version. Basically, they treat that as an interval. But we don't do it here. We don't do it here. Okay, we don't find the first and the third quartile of group data interval in this course. Do you know why? Okay, well, how many of you actually listening to me right now? I don't know, but that's fine. As long as you watch the recording, because we don't even find, we didn't even find the median. Now, the procedure we did to find the first and third quartile, we always find the median first. Okay. Now, in the group data interval, let me show you what I mean. Group data interval looks like this. In this group data interval, we can't even find the median We can't even find the median. So if we don't find the median, we cannot go even further to find the first and the third quartile. Okay, now, that's what we meant by quartile system. Now some follow-up. There's a terminology called Interquartile Range. Interquartile Range. It's different from range itself. Range means the maximum value of the data minus the minimum value of the data. Okay. From our last example, the maximum value is 10. From our last example, the maximum data is 10. The minimum data is 6. So, let's see. Yeah, the minimum data is 6. So the range is 10 minus 6, which is 4. Now, interquartile range is the third quartile minus the first quartile. Okay, so from example 5, interquartile range is equal to Q3, which is 8.5 minus Q1, which is 7. Q3 minus Q1, that's 8.5 minus 7. That's 1.5. Now, there's another thing called box and whisker, box plot. That's a diagram that tells us 5 gives information on the minimum, first quartile, median, third quartile, maximum. Now, they call that box plot because it looks like this. They call it box plot because it looks like this. So let's say they have a rectangular coordinate system. Okay. And this one here is, let's say, this is 6. This is 7. And this is 7.5. Is it over here? Yeah. This is 8.5. This is 10. Yeah, for the data we have in example 5, right? Okay. So instead of giving you the minimum is 6, the median is 7.5, the maximum is 10, they just draw it this way. Okay? They just draw it this way. So the smallest number here, that's the minimum. This is the minimum. Let me use another color. This is the minimum. This is the maximum. This is the first quartile, this is the third quartile, and this is the median. Okay, Now we call that box plot because we have a box that is the plot of these 5 important numbers. We also have another name for this. I believe that's called box whisker. Let me confirm. I don't really use that terminology, so I might be wrong. Yeah, box and whisker diagram. Also known as box whisker. Box whisker plot, box whisker diagram. Okay, but what I tell you here about this box plot is about how to read a diagram. So you can do many examples, right? But it's in the end, you know, it's about memorizing what this diagram means. Okay, it's about memorizing what these diagrams mean. Now, furthermore, the following is not just to enrich you with some knowledge. Beside quartile system, there are also percentile and decile. Now, quartile system is the most well-known system out of these 3. And then the second most used is percentile. Decile system, most people don't even know there's such name. Okay. But the percentile system basically partition it into 100 parts. Into 100 parts. Into 100 parts. Okay. If quartile system denoted by Q1, Q2, Q3, then percentile systems denoted by P1, P2, P3, up to P99. Okay. So P3 means what? That's the 3rd percentile. 3rd percentile. So imagine if you have a box, right? Imagine if you have a box and then you cut it into 100 parts, right? Now, P3 here means approximately 3% of the data set lies below or equal to P3. Okay. Approximately 3% of the data is less than or equal to this P3. Okay, now P99 means it's better than 99% of the data set. Okay, so imagine if somebody say, oh, that person is in the 99th percentile. When we say that person is in the 99th percentile, means that person is here. Okay, that's 99th percentile. Means that person is better than 99% of the data set. If that person is in the 98th percentile, 98th percentile means that person is located here when we say 98 percentile. Okay, means that person is better than 98% of the data and only below 1% of the whole data. Okay, now decile cut into 10 parts, partition into 10 equal parts. So therefore, you will see D1, D2 only up to D9. Okay, yeah. For quartile system, we need to cut it into 4 equal parts, right? So imagine if you have a box that you need to cut into 4 equal parts, how many times you chop it? 1, 2, 3, right? Okay. For you to have 4 equal parts, you need to partition it. You need to have 3 partitions. That's why you get only Q1, Q2, Q3. To have a percentile system, to have 100 parts, you need to have 99 partitions. That's why your P's start from P1 up to P99 only. Decile system, because you partition that into 10 parts, then you need to have 9 partitions, only from D1 to D9. Okay, now we don't really see decile system in real life. We see quite often percentile, but compared to quartile system is even more. Okay, percentile system usually being used if you want to show this person where is this person located. Okay, where is this person located? Like when they say, well, this person is in the 75th percentile, means it's better than 75% of the data set. Okay. Now that's for quartile system and the other variation of this quartile system. Also how to compute and find the quartile, first and the third quartile from raw data. Raw data but larger. Group data single point. Okay. Group data interval. We cannot find the first and the third quartile in this course because we didn't even find the median yet. Okay, we can estimate the median though. We can estimate the median. I wonder if I have my textbook on. Let me see, where's my textbook? I want to show you the formula that they use to find the median if you have group data interval. And therefore, you will see that's basically an estimate. Give me a second, I find it for you. This is from page, let me see what page is why I don't see the page number. Oh, they don't give page 96. This is from our textbook, Triola Elementary Statistics, 13th edition, page 96. Now, this is the formula they use to compute or estimate, to be more precise, the median of group data interval. Okay, now at least we still, even if we want to apply this, we still cannot apply this yet, because at least I need to teach you a couple things. I need to teach you what we call the lower class limit and class width, okay, which I'm about to do actually right now. Now, instead of teaching you into this formula, I will teach you how to compute or how to construct a frequency distribution. So let me continue in the next page, in the next section. How to construct frequency distribution from raw data with a large number. How to construct a frequency distribution from raw data if what we have is a large data. Let me quote from what we had earlier here. Oh no, I already wrote it. Okay, let me find the original. Let's say we have this as an example. How do we construct a frequency distribution from here? How to construct a frequency distribution from here? So I will make it into two columns here. The one on the left is the procedure that you will apply even for other examples, and what happened to this example here. The first step, you need to find the range. That is the largest data minus the smallest data. That's 96. Oh, I write actually, oops. What did I punch earlier? The range is the maximum minus the minimum. So in this example, the range is 104 minus 8, which is 96. The second step, the class width. Class width is denoted by W, which is equal to, class width is equal to the ceiling That's the notation, the ceiling. Now, if you see this notation, it means always round up. Okay, always round up. Yeah, depends on how accurate you want your class width to be though. But this notation actually round up to the next integer. To the next integer. But you can also say you round to the next one decimal place, okay? Which is equal to the range divided by number of classes. Now, the number of classes is always given. In the problem, okay? Suppose in this case, we want to construct a frequency distribution with 4 classes. Let number of classes is equal to 4. Let me make it 5. Number of classes is 5. Okay, then my class width will be 96 over 5. That's the ceiling of 19.2. Now, if I want to round it to the nearest integer, then it will be, not nearest integer, the next integer, then that will be 20. Okay, that's the class width. That's the class width. The third step, let M be the lower class limit of the first class, the first or small, the lowest class. So when I construct my frequency distribution, this is my X, this is my F, then M will be my lower class limit. Okay, now then the next lower class limit is the previous lower class limit plus W. Lower class limit plus W. So my class width is 20, so the next lower class limit will be 28. How do I get that? I add the width. Okay, I add the width. And continue doing so until you have, in this case, 5 classes. So I add 20 again, I get 48. I get 20 again, I get 68. I add 20 again, I get 88. Okay, so I keep on adding 20, adding 20, adding 20, until I have 5 classes. Next, the upper class limit of the first class is next next lower class limit minus 1. So I'm saying the number we should have here, that's 8 to what, right? This is 8 to what, 28 to what, 48 to what, 68 to what, 88 to what. Now, the upper class limit for the first class, is the next lower class limit minus 1. Okay, so I use 27 here. Now, it doesn't have to be minus 1, actually. It doesn't have to be minus 1 or minus 0.1 or minus 0.01 or other number. You can also minus 0.5 if you like. Doesn't matter. Okay, but basically you subtract some numbers. Okay, you cannot use 28 there. No, you have to subtract some small numbers. Okay, but of course, because you want to keep it simple, then I subtract that by 1. Okay, but you can, depends on the accuracy you want it to be. Then if you want to be up to 1 decimal place accurate, then you use 0.1. Okay, now the rounding that you use here, so if you decide to use minus 0.1 here, then you should round to 0.1 for the class width also. Okay. Basically, if you round it to the nearest integer, then you take the previous integer. If you round it to 1 decimal place here, then you use 0.1 accuracy, so on and so forth. Okay. Now then, from there, I continue further. I need to erase my yellow marking. So this is 27, this is 47, 67, 87. Now the thing is, the way we design it will make the upper class limit also have, you keep on adding 20. Okay, now the thing is that what happened to the last class? You also add 20. So this will be 107. This is 107. Even though the largest number we have in our data, the capital M, is 104. But we consistently add 20 for the upper class limit, just like when we add 20 for the lower class limit. Now then from here we tally it. The last step is we tally from the raw data. So we tally from the raw data. Let's see. So the first class from 8 to 27. From 8 to 27, there are 6 of them. The second class from 28 to 47, there are 11 of them. From 48 to 67, that's 17. From 68 to 87, they are 13. And from 88 to 107, they are 6. Now make sure you add them. And when you add, you make sure you add this manually. And the sum should match with the number of data you originally have. Okay, just in case you miss any one data. Okay, just in case you miss any one data. Do not think, oh, there are 53 data, then the sum here is 53. No. Count it. You add this just in case you miss any data. Okay, I want you to count this just in case you miss any data. Now let's review this. Let's review this. Okay, so the first step, I get the range, the maximum minus the minimum. Second step, I get the class width. That is the range divided by the number of classes. Now, the number of classes is always given in advance. So I will tell you, construct 5 frequency distribution with 5 classes, let's say, for example. Okay? And then you round up. Okay? Depends on how accurate you want that to be. Okay? Not accurate you want it to be. How many decimal places you want to use. The rule of thumb is because the data provided to us in integers, then we will round it to the nearest integer. Okay? Yeah. If the data given to us with, let's say, to 1 decimal place, then you may want to round it to the nearest decimal place. Okay, 1 decimal place, then you round it to 1 decimal place. If you have 0.5, let's say you have 0.5, 0.5, for example, right? Then you can round it to the nearest integer. Okay, you have some freedom there. It's just like if you have 0.5 here, it's accurate to 1 decimal place, then there's no need for your class width to be 2 decimal places. There's no need. Why? Well, even your data is not that accurate, that many decimal places anyway, right? Okay. So once you get the class width, then we start with the lower class limit in the first class. Our first class this is what we call the first class. And lower class limit refers to the smallest number you write in that interval. Okay, this is the lower class limit. And this is the upper class limit. Okay, now, so in other words, if I say, oh, what is the lower class limit of the third class? Then the third class is this, the lower class limit is 48, the upper class limit is 67. Okay. Now let's do one more example. Let's do one more example. Let me pick question from somewhere. Give me a second. Give me a second. Let me at least get a little screenshot for them. I forgot up to which part did I record it though. I think we did up to here. Oh, I think the last one I stopped here. Good thing that I will go over this later. Okay, so at least they have another example to look at. Okay, let's take a break, maybe 10 minutes break, and then after that you continue working on this. Okay, please do this though, please do this. Please do this. Because even though this is the second example for those who attend the class, this may be the only example you get if you are only watching the recording. Now, one of the main reasons I want to go over this right now, because this type of question actually what you see in the first page of my test one. Okay, so this problem here, this data here, actually from one of my test one, I think it's spring 17, or one of them. Okay, let's start. What's the median? Let's see how many data here. 1, 2, 3, 4, 5, 6, 7, 74. So n equals to 74. So the median will be 74 plus 1 divided by 2. That's 37.5 data. I need to look for data number 37 and data number 38. 37, 1, 31, 2, 3, 4, 5, 6, 7. So data number 37 is this one. 38 is this one. So 45 and also 45 here. So the median is 45 plus 45 over 2, which is 45. So again, basically means the median is between these two numbers, right? The median is between those two numbers. How about the mode? How about the mode? 45 happens twice. Is there anything happens 3 times? Is there anything happens 3 times? Yes, that's right, 32. 32 happens 3 times. Is it the only one? In case I miss it. Yeah, only that one, huh? Okay, now then the first quartile will be the number of data less than the 37.5. There are 37 data in the lower half. Let me write it down. 37 data in lower half. So 37 plus 1 divided by 2, that gives us the 19th data. Data number 19 is 24. And data number 19 from the top is 14, 15, so 14, 15, 16, 17, 18, 19. So data number 19 from the top, that is 67. In fact, even if I count it from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. You still get 67, right? Okay. Now then, I will construct a frequency distribution with 4 classes. Space, let me just do it here. So, frequency distribution with 4 classes. Part E. The range is 99 minus 0 is 99. So the class width is 99 divided by 4. That's 24.8. And I always round up, so I get 25, right? So the score is, the minimum is 0, and then this is 25, this is 50, this is 75. This is 24, 49, 74, 99. The frequency will be from 0 to 24, there are 19. 25 to 49, that's 22. 50 to 74, 21. And 75 to 99 is 12. The total of 74. The total of 74. Okay. Now then, let me continue for part E. For part E, we'll extend the table. So lower class limit, upper class limit, lower class boundary, upper class boundary, and then, oops, sorry, and then relative frequency. The first two columns too easy. 0, 25, 50, 75. Okay, recorded yet. And then this is 24, 49, 74. Lower class boundaries. Upper class boundary for the first class, that's 24.5, which is shared with the neighbor. Upper class boundary for the second class is 49.5, which is shared by the neighbor. The upper class boundary for the third class is 74.5, which is shared with the neighbor. And then the lower class boundary for the first class is negative 0.5. Okay, and then upper class boundary for the last class is 99.5. Relative frequency, that's 19 over 74, 22 over 74, 21 over 74, 12 over 74. The total is 74 over 74, which is 1. Okay, now I hope this is what you get also. Now, you may have an issue with this though, but Thomas, that's a test score, right? So they should not get negative numbers. Should we just keep it 0 there? That's the boundary. Well, the answer is no. The answer is no. Two reasons. First one, I just apply the procedure. Okay, I just apply the procedure. So regardless the fact that nobody get negative score doesn't make it the boundary change. No. Okay, that's one. The second reason is actually I did give negative test score. Okay, I did give negative test score. So that was the case when the student actually get everything wrong and didn't write his name. So I penalized half point for not writing name, and then I need to search who was the person who took the test but get everything wrong and not writing his name. Now you may wonder, Thomas, why do you want to penalize that person with half point while that person took the test? Why don't you just give 0? Here's the thing though. Here's the thing though. I need that person's for attendance, right? Okay, I need to, so if I don't look for that person's name, that person will lose his attendance, and I may even drop him. So in that situation, I mean, this is actually what happened sometime in the past. Okay, it happens in the past in my stats class at East LA College. Somebody get negative 0.5. Okay, so we just do the procedure. Going back to the theory, we just do the procedure. Okay, it is not, we don't need to worry about, hey, you know what, nobody get negative number. Hey, you know what, according to procedure, that's what it's supposed to be. Okay, now if you say that this is the age, right, the age of people, then still, I will still do it this way. But Thomas, nobody can have negative age. I understand, but I just do the stats. Okay, I just do the stats. Okay, I do not want to start the consideration. I know it sounds doesn't make sense, but then when you try to put too much sense into it, what makes sense for you doesn't make sense for me. There's the thing, okay? And it distorts our statistic later on with opinion. Now the thing is, when I write that statistic and present it to somebody else, people will see the statistic without seeing the opinion that you put in there. So leave your opinion at the door when you do stats. Okay, that's what's supposed to be. Of course, in reality, one thing you can do as a statistician to affect the outcome is present some data. Okay, like for example, the one I was talking about here. Okay, this supposed to be negative 0.5 there. But of course, people can argue, Thomas, when it comes to test score, it cannot be negative. Notice that that's opinion. Okay, it may very well reflect the reality. Okay, but it's not really within the standard procedure. Okay, so once you change this into 0, for example, instead of negative 0.5, okay, and you present it to other people, then other people will not see it that way. Other people will not see your opinion. They just see the statistic. Okay. In other words, you insert your opinion into the statistic and present that wholly as a statistic. You see? Okay. You already pick and choose. You already pick and choose what makes sense for you, what doesn't make sense for you. And then you only present those which make sense in your opinion, and you filter out those that not make sense. But when other people read your report, other people read your statistic, they didn't know that you already filter out those not make sense. Okay, so if I try to picture it, how the data being manipulated is this. Okay. Let's say this is all the data. Okay, and then you come and look at that, you say, oh, you know what? This number here very likely is wrong, so I don't input that. this number here is very likely is wrong, so I don't input that. Then you only process all those informations within this yellow color. Because in your opinion, there are some data that doesn't make sense. But then when you process this data and report that maybe in the news to somebody else, then they only see the yellow one. Those reader, those audience will not realize that you already filter out some numbers which in your opinion doesn't make sense. Okay, so you see that you use your opinion and prevent other people to see those data. Right? Now, don't get me into politics because I can say so much about politics, how both sides, Republican and Democrat, use statistics to the point of abusing it for their own purpose. Okay? But I don't blame them too much, or also accept that they don't, they're supposed to say if they already insert their opinion, but notice that that's how they make money, right? Okay, they need to come up with statistics that is favorable for their employer, okay, so that they can keep their job, and using that statistic to influence people's opinion. Okay, but as your stats teacher, I want to tell you that one way to distort the outcome of statistics is by putting your opinion. You judge the data, what is reasonable, what is not reasonable. Unfortunately, your opinion does not reflect in the statistic. So other people only see that as the data that you process, but other people will not see that you already filter some data. On the other hand, we as the audience, okay, you also need to realize that our news company, okay, the journalists may not be the news company, the journalists may insert their opinion as a fact, may present their opinion as a fact. They mix it together already, okay? Now, then when we read, you need to be able to kind of like split the hairs, like, oh, you know what, this is opinion. You know what, this is actually the fact, okay? Let me tell you this. Thomas had an accident. That statement can easily be verified. Okay, you can ask Thomas or hospital or look for a police record, Thomas have an accident. Okay, now let me show you how people insert their opinion. That Thomas had an accident. The fact is Thomas had an accident. You can verify that. But in that fact, the journalist or the reporter already insert his or her opinion about Thomas, mixing it together with the fact, his opinion, mix it together with the fact, and the reader may subconsciously take this opinion as a fact. Now, if you read this kind of statement in the same article, let's say 10 times, eventually that person, the reporter, would influence your subconscious and change your opinion about Thomas. So it's not about accident anymore. It's about Thomas being bad. You see what I mean? Okay. So this kind of words is the one that when you read that, you say, hey, you know what? If you want to talk about the accident, Thomas have an accident, just say Thomas have an accident. Okay, you don't need to say that bad Thomas had an accident. Okay, if in fact, bad Thomas has a small accident. And in that small accident, he lost his limbs. You don't call that small accident. The word small there is opinion. Okay, just say that Thomas had an accident, he lost his limbs. Okay, and let the reader decide if it is big or small. Because lost his limbs, if I lost my limbs in accident, that's a very big deal for me. But compared to those people who have accident and lost lives and that person's and family's life, of course, compared to that, this is a small accident. Okay, but saying that Thomas has a small accident where he lost his limbs, it's like you mix facts with opinion there. Okay, leave it out. Now you as a reader, okay, need to be able to know how people present facts and mix it with opinion. That's why when you go to the court and they ask you to swear, they will ask you to swear this way: I will tell the truth, all the truth. The emphasis is on the word all, which means you don't hold any information back. Okay? Nothing but the truth. Which means you don't tell the truth and insert together with that lies. Okay? So how people lie? People lie by one way, holding back informations. You tell the truth, but not all the truth. Second, mixing truth with lies. Now, the good thing of being journalists or reporter, they are not held in with this standard. Okay, they are not held with this standard. I should say this one here. They are not held with this standard such that at times they hold back important informations. Okay, and at times they mix truth with opinion, which may be lies. The thing is, your opinion depends on where you stand in that situation. Okay, and that's where you start filtering out some informations, you start mixing something else in. Now, you as my student, regardless where you stand in your political spectrum, regardless where you stand in your daily life, okay, I want you to learn, at least learn how people actually distort informations. If you want to use that, up to you. I don't teach you moral. Okay, my job is to teach you how we apply statistics and how people lie using statistics. Okay, to say it in a very bad way, if you need to lie, just do it. Okay, but at the same time, I want you to be somebody who can detect somebody lying. So instead of somebody do it to you, how to say it? It's like if somebody lied to you, you can detect that. But if you need to lie to somebody, how do you make it in a way that nobody can detect that? Okay, again, I don't teach you moral. I teach you stats. Okay, learning from how people lie using stats, and you know how people can try to lie to you. Okay, and learning how people lie to you, you also learn who knows you want to use it, right? But no, of course, I don't encourage you to lie though. Okay, but at least you need to learn how people lie. Okay, now I'm not done yet. I still have around 20 minutes, 25 minutes to be more precise, but at least I want to go further into this. I want you to realize what we have done. Once we get this frequency distribution, the next follow-up question is extend it to find the mean and standard deviation. Extend, copy, and extend. So I have follow-up question right now. Copy the frequency distribution in part D and extend to find the mean and standard deviation. So what I will do first, I will copy that first. Okay, I will copy that first. And then I will extend. If this were my x, if this is my x, then the first thing is xi, right? After xi is long time no see. After xi is fxi. After fxi is xi squared. And after xi squared is fxi squared. So I hope you realize at this point that what we did before suddenly come back as a big package. So the xi here will be 12. That will be 37, 62, 87. Do you want to do this? Work this out first instead of I do it by myself? Okay, let me give you 5 minutes for this. Okay, and don't forget, this is a sample, I believe. Yeah, this is a sample. This is a sample. So you need to find basically the sample mean, sample variance, and then sample standard deviation. Okay, now let me give you 5 minutes for this. Okay, let me start. Okay, 19 times 12 is 228. 22 times 37, it's 814. 21 times 62, 1302. 4 times 87, 1044. So I add all of these. I get 3,388, such that my sample mean now is 3388 over 74 divided by 74. That is 45.78378. Let me go on. X squared, this is 144. 4 squared is 144 times the frequency, 2,736. 37 squared is 1,369 multiplied by 37, 50,653. 62 squared, 3,000. Hold on, I think I multiplied it incorrectly. The last one, that one is not. This one is not. So it should be 1,369 times 22. 30,100. 3844 times 21. That's 80,000. 724. 87 squared is 7,569 multiplied divided by 12. That's 90,808. So I add 80,724, 30,180, 2,736. I get 204,406. Now then, samples variance will be 74 times 204,408 minus 3,388 squared over 74 times 73. Now, if you are working on this also, please check my work. I get the variance, oops, the sample variance to be 2,799.45502. Therefore, the sample standard deviation is the square root of that number. That's 52.90988. Which is actually quite big though. So, you know what? Let me check my computation. I somehow feel like I've made a mistake somewhere. 144 times 9Q. That's correct. 37 squared times 22. That's correct. 62 squared times 21. That's correct. 87 squared times 4. That's correct. Well, anyway, so that's the standard deviation. I still don't think that's the number supposed to be. I didn't expect that standard deviation to be that big. Even though it's possible. Yeah, 74 times 73 at the bottom. That's right. So, hold on. Did I multiply that incorrectly? 204,406 minus 3,388 squared divided by the product of 74 times 73. Ah, yeah, that's right. That's incorrect. Yeah, see? So my computation was, my number here is correct, but my number here is incorrect. Thank you. So after I computed it, that's 675.21288. Is it what you get also? Who's that? Stephanie?
I'm still a little confused.
Which part?
I thought it was n minus 1.
Yeah, that's right. Yeah, at the bottom. So the n is
So
74,
it's
right?
73?
74
Yeah.
times 73. N times n
Oh,
minus 1. N times n minus 1.
oh, and times n minus 1. Okay,
Uh-huh.
I get
Yeah.
it.
Yeah. Uh-huh. N times n minus 1.
Okay, thank you.
Okay. Uh-huh. Uh-huh. And then, well, but thanks for your correction earlier. I get 25 point. Now this makes more sense. This is 25.98486. Okay, I would actually like to stop here, but let me just go on a little bit more. Some definition. Definition. Usual interval in my class, in this class, is defined as the interval within 2 standard deviation of the mean. Okay. Now, in practice, we use this definition. When n is large, larger than 30. The larger the better. The larger the better. Okay. Now, what happens when n is less than 30? Then we use other definition, which I will not teach you, or at least not today. But what does this imply? Going back to that example we have earlier, okay, what is twice the standard deviation away from the mean? So if this is the mean, you add twice standard deviation, and you subtract twice standard deviation from that mean. That will give you what we call usual interval. Okay, so the lower fence refers to this one here. This is the lower fence. The lower fence is the x bar, which is 45.78, 45.78378 minus twice the standard deviation. I get negative 6.18594. Now the upper fence, let me use green, let me use this color here. The upper fence is the mean plus twice the standard deviation. I get 97.75350. Okay, so the usual interval in interval notation, if I write it in interval notation, is negative 6.18594 to 97.75350. Then another definition, outlier. Outlier is defined to be is the data or are the data outside of usual interval. Okay, outlier is the data outside of the usual interval. So if we look back to this information here, this data here, if we look back to this data here, okay, yes, we have people doing poorly, and we have people doing very well. Okay, now then how do we decide which of them is actually break the curve? Okay, are these people the one not doing well? Okay, so poorly, or these are the people doing too well? How do we decide? Well, it can be both, of course, right? Now, the thing is, we should not put our opinion, like what I said earlier, we should not put our opinion into judging the data, at least not for now, okay? We don't have that skill yet. And we try to avoid having our opinion though. So what I will do is I use this whole data, this data set. I will use this data set. I will use this data set to be the judge. Okay, so how do we know that Thomas test is too easy or Thomas test is too hard, for example? Okay, so you look at the test score, right? You look at the test score, and then from there you see, if you have outlier, which outlier will that be? Okay, so with this kind of test, you see that the usual score is in this interval, the usual interval. The score should be in this interval. Okay, now then, if we look back to this data, okay, which of them is outlier? You see, the lower fence is -6 something, so this 0 is considered quote unquote usual. We don't like that, of course. It's not a score that a lot of people get, so not in that sense of usual, okay, but comparatively to everybody in this, all the numbers we have here, okay, the 0 is within that usual interval up to 97.7 something. Okay, look back here. Okay, so the outliers are those who get 98 and 99. Okay. Yeah, they vary too far. These two numbers varies too far from the mean, and we consider that as an exception. Okay. Now, even though 97 is only 1 point less than 98, but this 97 is not considered unusual. Okay. However low you think this 0 is, but compared to everybody here, that 0 is not unusual. We don't like that. Of course, that's quite far from the mean, right? But looking at the standard deviation, which is quite big, only 5 points, okay, then that 0 is not unusual. Okay, so you see that how I decide that it is usual or unusual. The only thing that we put in, and this is one of the rules that we follow quite widely, is that we define usual interval for any situation when n greater than 30 to be that it's twice standard deviation, the interval within twice standard deviation within of the mean. Okay, that's decided way earlier. So I don't look at the data first and then decide. No, we have this rule even before we look at the data. Okay, then when we have the data, I just process that. Okay, I just process this data like usual. Okay, and then I go on further, get the usual interval, and then get the outliers. As if we are saying, is it strange if you change this course here becomes the age of people coming to Thomas classes, then it seems like it's not strange for a baby come to my class, but it's quite strange for somebody 98 or 99 years old come to my class. Okay, they are outliers. Okay, they must have had a big dedication to come to my class. Okay, not that I say that those 0 or 2 years old coming to my class not doing a lot of effort, but compared to the mean, compared to the rest of the class, it's not too much. It's not significantly different from the mean. Okay, this is where I will stop. And you can start working on the first 1.5 page of all my test 1. This is week number 2. This is week number 2, and your test 1 will be week number 5, as I remember. Okay, but you can start studying already from my old tests. Okay, page 1 and half of page 2. Page 1 and half of page 2. Okay, then this is where I will stop. See you next week.